Good afternoon, everyone. Welcome to today's webinar presentation. I'm just looking at the logins here. Looks like people are still signing on. A lot of people are still getting settled. So we're just going to give it a few more moments before we begin the official broadcast here. Thanks for being on time and thanks for your patience. And for those that just all signed on there, just be patient with us. We're going to start the official broadcast in a few more minutes. A lot of people are still getting signed on here. So thanks again for being on time. Well, welcome everyone to today's Veolia Water Tech Talk. My name is TJ Willits with Veolia Water Technologies. I'd like to welcome you to today's broadcast about proactive odor H2S control for municipal and industrial facilities here. Just some housekeeping items. You should be hearing me speak now. If you are having any issues with your audio, there's two ways to listen in on today's presentation. The first one is likely what you're going to be using. It's the computer audio, so you could listen through your headphones or speakers. If you're having any issues with that particular audio source, you could actually call in and switch, click the button for phone call, and it'll give you a call-in number and a login to be able to listen to the broadcast via your phone. Everyone is muted today on today's presentation. There's a lot of people attending. Also, for those wanting to watch the presentation afterwards, or maybe a colleague that missed it, the webinar is being recorded and will usually come back to your inbox within 24 or 48 hours after the live broadcast. Now, even though everyone's mics are muted, we wanted to make this presentation as interactive as possible. So you'll see on the right side of your screen the ability to type in a question through the question box or the chat box. So feel free to submit questions throughout the presentation, and then we'll try to get to as many as possible at the end of today's presentation as time allows. So just one other thing to make everyone aware of, looks like there's a lot of people within the pulp and paper industry on this call, as well as several other industries. But if you're interested, we have a pulp and paper specific webinar called Advanced Water Reuse, Fiber Recovery, and Wastewater Treatment Strategies. And that's going to be on Wednesday, February 22nd. Feel free to go to our website and register for that after today's broadcast. We'd love to host you again. Also, an amazing resource of technical information. If you go to our website, we have an on-demand webinar section. We have about 60 webinars that we've collected over the years that you can go ahead and watch and about a variety of different industrial and municipal topics. So I encourage you to check that out when you have a few moments. Now, if you're looking to use this particular education opportunity for some continuing education certificates or something like that, we will send out a participation certificate, and that'll come within 1 or 2 days after the webinar. So be on the lookout for that. It's just a PDF that you could use for your documentation. And something fun, if at the end of the broadcast, everyone will be taken to do a survey. It takes about 3 minutes, but it really helps us improve the quality of these Veolia Water Tech Talks. So just to have a little fun, everyone that takes the survey after the live webinar will be entered into a raffle to win a $25 Amazon gift card. So thanks again in advance for helping us with that. So a little bit before we get into the main presentation about Veolia Water Technologies, is we're a leading water and wastewater treatment provider, and we support our customers on those 3 pillars that you see there on your screen, through projects, through engineering and procurement of projects, by providing innovative technologies related to water and wastewater treatment, and also supporting our customers through a wide range of services. We support all the industries, industrial, municipal, and you can see them listed there on your screen. And now to transition to today's technical portion of today's presentation here. I'll go through a little bit of the agenda and then I'll introduce you to our speakers. But today you're going to learn a little bit about the background and risks of odors caused from H2S. And then also we're going to go over some common strategies for odor control that you may be familiar with or may be using at your particular facility. And we're going to spend some time talking about the Hydrex Sulfide Elimination System, or H2S or HSES, this new approach for H2S treatment. We have some case studies and data to share with you at a variety of industrial and municipal facilities. And then we'll also talk about some first steps in going through and executing an odor control project. And as I said before, any remaining time, we'll try to get to some questions that you may have throughout today's presentation. So at this time, I'm going to introduce you to our two panelists that we have here today. The first that you'll hear from is Phil Mateo. Phil is an application manager at Veolia Water Technologies, and he provides technical support to several industrial customers. He has more than 33 years of water treatment experience and 15 years of experience related to H2S and odor control. Phil's primary focus is chemical treatment of water, wastewater, and cooling systems, along with the automation equipment needs to support that area of water treatment. Phil has a bachelor's degree in chemistry from Syracuse, along with his MBA. The second speaker that you'll hear from today is Jeff Privet. Jeff is a Hydrex product manager and is responsible for supporting clients by providing support, solutions in several water treatment areas, which include clarification, filtration, of course, odor control, Sulfide treatment through Veolia's Hydrex chemical service offerings. He has more than 20 years of experience in a wide range of water and biological wastewater treatment, and primarily he focuses on municipal customers. So at this time, I'm going to hand the webinar presentation over to our first expert panelist, Phil Mateo. Phil, are you with us?
I am here. Thanks, TJ. What I want to do is start with the background and some of the risks associated with H2S. H2S is known as hydrogen sulfide, is the most common odor-causing chemical in the industrial and municipal sectors. In the municipalities, typically at their water pollution control facilities, H2S could be found at the headworks and can be found inside the biological wastewater treatment processes, typically tertiary and sometimes secondary treatments. It's also found out in the collection systems and the lift stations that are out in the community. In the industrial sector, we'll talk about H2S that's both biologically and chemically produced in the pulp and paper mills, refineries, chemical plants, and the oil and gas sector, both upstream and midstream. And then the food plants, textile plants, ethanol, landfills, basically anybody else who has wastewater or a wastewater treatment facility is likely to have or has had H2S as a problem at their facility, either as a safety issue or it's just as an odor. H2S is a colorless gas that's heavier than air, which means that it's going to fall to the low point of any container or any vault or any tank or rail car or anything else. It's typically in our sector, in the water sector, it's created by sulfate reducing bacteria who reduce the sulfate to sulfide in an anaerobic environment. The sulfide then escapes from the water solution in the form of hydrogen sulfide gas, which is H2S. Most people recognize that it's H2S due to that rotten egg odor. The sulfide itself typically forms biologically when dissolved DO levels drop below 1 ppm. When a sulfate molecule is reduced by the bacteria, it becomes a sulfide. Sulfide remains in solution even when the DO levels return back up into an aerated state. The sulfide is always in solution. There can be no H2S in the atmosphere until their sulfide has formed in the water. When I talk sulfide, we're really talking three different species within the sulfide. The first is H2S, which is hydrogen sulfide. The second is HS-, which is known as hydrosulfide. And the third is just straight sulfide. And the form of that sulfide is determined by the pH of the solution. As the pH increases, the sulfide will be prone to stay in solution. When the pH drops, however, sulfide will easily off-gas as an H2S gas. So the lower the pH worsens the odor problems as more H2S is released, and the higher pH hides the problem as the H2S is converted to sulfides and it remains in solution. One downside of the higher pH, though, is that deposition can occur. The chart on the bottom right, the purple area demonstrates or is indicative of a water solution where there is a equilibrium between the H2S, the HS minus, and the sulfide, and that is pH dependent. Then we have the dynamic between the H2S that's dissolved in the water as aqueous H2S with H2S that's in the gas. The only thing that would create the H2S gas is the H2S aqueous that is in the solution. Temperature has an effect on H2S as well. So as the temperatures rise, H2S can escape the solution more easily. As the temperature in the air or the water rise, typically the DO levels in the water decreases, which leads to more anaerobic conditions, which favors the production of H2S. This is why we typically see odor complaints and some corrosion issues are magnified during the warmer months. The H2S in the air is driven by the amount of H2S in the water, the temperature, and the pH. This chart here shows that even at a room temperature of 25 degrees C, 1 ppm of H2S dissolved in the water can create up to 250 ppm of H2S in the air. So it doesn't take a whole lot of H2S in the water to create a whole bunch of H2S in the air. The effects of H2S are several, but the first one we'll chat about is the health risks. The chart on the left is a common chart that talks about the lethal spectrum of H2S. In less than 1 ppm of H2S, your nose can smell that it's a sulfur compound. It smells that something smells a little bit sour. And then typically 3 ppm or more, it's very clear that rotten egg odor is an offensive odor. When you get up to 10 and 20 ppm in the air, now you're in the areas that are regulated by OSHA. Anything beyond 20 ppm, you're really supposed to leave the work area. So again, a little bit of H2S in the water can force a situation where people will be getting headaches, they'll be nauseous, they'll get throat irritation and eye irritation. At 100 ppm, you go into olfactory paralysis, which means you don't smell the H2S anymore. And that's very scary. If you're in a situation where you're smelling it and then you don't smell it anymore, you may be losing your ability to smell the H2S. Get up to 500 to 1,000, you're in a situation where people can die. On the bottom right corner, I want to show that orange 4-gas analyzer. And I just want to stress to everybody, if you work in an environment where you're going to have H2S or low oxygen or anything else that's a safety issue, please carry a 4-gas monitor with you. Every year in the United States, several people will die from H2S exposure. Typically, they're workers that are working inside a vault, inside a tank, inside a rail car, something like that. And typically, they die in at least pairs. First person goes in and gets overcome by H2S gas. Second one rushes in to try to save them, and they die as well. So I started with the health risk because everyone needs to be aware. This isn't just a nuisance odor. This is something that's very dangerous. Now, besides the health effects, what does H2S do to your infrastructure? In a pipe, whether that pipe is in a chemical plant or a refinery, wastewater in a community, the sewer system, the H2S will off-gas from the water and go up into the headspace of this pipe or a vessel. And there, it'll be biologically oxidized to sulfuric acid. And that sulfuric acid will corrode whatever is there, so either the metal or the concrete. So the metal and the concrete, the steel and the concrete in the treatment plant, the wet well, gravity mains, will start to corrode away because it starts with the H2S. The copper components of electrical systems inside buildings generally rapidly oxidize and get destroyed. We know when we have problems with H2S, when you open up the MCC panel within the facility and find that all the copper lines are corroding with a black coating, that means that you've got H2S corroding away the copper, which leads to system failure. The graph, the chart on the left was put together by the EPA trying, as they did their research into the effects of H2S on equipment. And what the chart, these numbers may not be exact, but what the chart is trying to show you that is even a little bit of sulfide in the system can reduce the life expectancy of the pipe. So at 0 to maybe 0.5, half a ppm of sulfide, you might expect to get 30 to 50 years of life out of a pipe. But when you get down to 2 ppm or so, you probably have reduced the life expectancy of that pipe. And when you get down to 4, 5, 6, 7, now you've greatly reduced it to now it's only going to last 4 years. Now the pictures on the right show 2 metal pipes that were corroded away. The upper right shows a manway where the concrete and the metal steps had corroded away. And then on the bottom right is a classic example in the municipalities of crown corrosion. And that's where a sewer pipe collapsed from the failure due to the H2S corrosion. And quite frankly, when this occurs, it almost always happens while a heavy vehicle is driving over it. So now you have damage to vehicles and potential death of individuals that are driving through that area. There are common strategies to treat the and I'll call it H2S control. The first obvious one is design. Design the system to reduce the chance of H2S production. Most plants, when they're brand new, that's already been ingrained, but as things change, as things grow or shrink, the design may not have been enough. So the next step we typically see is what's known as capture and treat. And that's where we're capturing the air phase and then treating for the H2S in the air phase. The next one is treating it in the water phase. And typically that's adding chemistry into the water stream that has H2S to either prevent the formation of H2S or to react with the H2S that's already in the water. The last grouping of sludge treatment is very similar to water treatment, but it is specific. There's a few nuances when dealing with sludge that's slightly different than what you do with water. Within the design, properly sizing the infrastructure, making sure you don't oversize the wet wells or the pumps or the force mains. You want them to be reasonably sized so that you get good, common, continuous flow through systems where you can, and you reduce the amount of holding time of water that will stay stagnant in a pipe. In that stagnant areas where H2S starts to develop. Flow management is another one they try to do, is to minimize the peaks and valleys in the flow. In some low flow lift stations, they'll even add an aeration pump or maybe a diffuser to increase either the dissolved air or the dissolved oxygen levels. With municipalities, they usually have one more step in trying to design out H2S formation, and that's by talking to the industrial plants that are contributing to their waste stream, and that is known as the pre-treatment program. And in those areas, they're typically asking the plants to not descend to H2S or to reduce the BOD or COD loading from their particular industrial plant. So if the engineering or design is unable to prevent the H2S, other treatments may be needed. Capture and treat, again, is where we're taking that air and we're attacking the H2S that's in the air. One way to do that is carbon filters, where the air passes through a media of carbon. It gets absorbed into the carbon, and the air that leaves it is relatively free of the H2S. Now, it definitely works, and it'll take not just H2S, but some other malodorous compounds. The downside is once that media is spent, it needs to be changed and it needs to be disposed of. And many times that's disposed as a hazardous waste. So depending on the H2S concentration, those media swaps could be fairly often. The one that's most commonly seen is the wet scrubber or the wet chemical scrubber, where there's a packed media inside a scrubber with water being sprayed down on top of it. that water contains a high level of sodium hydroxide, caustic, and bleach. And the idea is to raise the pH so that the airstream that's pushed through the scrubber will transfer the H2S from the air to the water phase, and then it's oxidized. It works, and it can treat a wide range of reduced sulfur compounds, so it'll do H2S and mercaptans. Downside is they're typically peaked at about 50 ppm. You do have a feed of caustic and chlorine, so you have to handle those hazards, and there's some significant capex. Biofilters is considered a green technology, and that's where there's a wet organic substrate, typically wood chips or something similar. They're kept constantly wet, bacteria grow in them, and when the airstream goes through the biofilter, the H2S is absorbed onto the water. The bacteria then degrade the compounds. Again, it's considered a green technology, but it's very, very vulnerable to peaks and valleys of H2S production. And so the bacteria want a steady supply of H2S, and if you have variable conditions, that can mess up the ability for those the bugs to be viable. So on the chemical side, one of the areas is pH control, simply adding caustic or magnesium hydroxide to keep the pH up above 8.5, and by doing that, reducing the H2S from off-gassing. The pros are a majority of those sulfide species will be entrained in the solution all the way to waste treatment. And if the waste treatment plant is in need of additional alkalinity, the pH control may provide it. However, some of the downsides is the downstream untreated sewer laterals will reduce the pH back to neutral as it commingles with the treated water. Once the pH goes back down, you get the H2S off-gassing. And the chemistry, caustic and magnesium hydroxide, does require special feed containers. A different approach is the use of calcium nitrate. The bacteria naturally want oxygen from the water, and if there's not enough dissolved oxygen, they'll seek out nitrates, and they will strip the oxygen off a nitrate. If they can't find nitrate, they go after sulfate. So the idea here is by adding a preferential oxygen source for the bacteria, they won't go as far as sulfate reduction. It is easy to use, safe to handle, and it's successful in multiple feed points where there is less than 10 hours of hydraulic retention time. But beyond that, it creates a problem. The downside is it does require a large volume of chemistry, so you do have an elevated OPEX. It's got to be added upstream of the sulfide formation zone, and it may exacerbate the FOG in the wet wells as we are promoting the growth of bacteria in the system. We're going to increase the slime layer formation in the pipes and in the wet wells. Another approach is to precipitate sulfide using iron salts, and that could be ferrous or ferric chloride and ferrous or ferric sulfate. And so we're precipitating the iron as a iron sulfide. It's very economical per gallon for iron salts, and it works very quickly. But the downside is it produces a large amount of solids, so there is going to be an increased sludge production. And as this is fed, these solutions are dissolved, these metals are dissolved in an acid solution, so the pHs are low. So it does lower the pH of your water, and it does increase the corrosion potential. Another technique has been around for a while is using chlorine or something similar. So chlorine gas, sodium hypochlorite, some sort of chlorine product. And what we're trying to do is to break down the organics and oxidize the H2S. It can oxidize those sulfides and some of the organics that are in the water. But the downside of this is it's not specific to H2S. Therefore, it's going to oxidize anything it can find in the water. So therefore, it's not a very efficient treatment solution. A slightly different approach is peroxide. This is a direct reaction between the peroxide and the hydrogen sulfide to produce elemental sulfur and water. And so this solution is stable, and the sulfide that's created is not able to off-gas. It is a strong oxidizer that will oxidize the sulfides relatively quickly. And again, the only byproducts are oxygen, water, and sulfur. Downside is high volumes may be required to treat the H2S alone. So you may need a lot of product. And next one. The last one is what we call a grouping. A general grouping is called scavengers. And these are things that react with one of the sulfides and keeps it locked up in solution. Common ones over the years are things like triazine and glyoxal. They're a bit more specific to H2S. They're definitely common in the refining and downstream oil and gas industries. They are more expensive. And another downside is the municipalities are typically not familiar with them and are less likely to want an industrial site to feed it into their outfall go into a municipal treatment plant. I mentioned sludge treatment earlier. So in sludge handling areas, there's a high potential for H2S to be an issue, especially in sludge holding tanks that do not turn over very often. And the treatment approach is pretty similar to the methods that we use in the water phase because we are treating for the water that's in the sludge. So we have sulfide scavengers. We got mixed oxidants. And then we have iron salts. So they all have their own pros and cons that we mentioned earlier. But a couple of things to keep in mind in relation to sludge is we need to make sure that we understand that we could interfere with the coagulation process in a physical chemical treatment plant, and that we may be adding additional sludge to this system. The crux of what we're going to talk about moving forward, and Jeff is going to present this, is a new approach for H2S control, and that's what we call the Hydrex Sulfide Elimination System. Jeff?
Well, thank you, Phil. So after showing you many different methods and strategies for odor control, we want to tell you about this new approach. And with Veolia being the leading global water and wastewater treatment and operations company, we needed to identify a solution that is highly effective at targeting H2S to protect that human safety and prevent infrastructure damage. Something that was flexible and seamless to integrate into various applications, economical for the client and end user, and very scalable to different levels of treatment. So the Hydrex Sulfide Elimination System is an effective and regenerative sulfide removal process for a variety of municipal and industrial applications, bringing together that simple approach with proper engineering, equipment, and chemistry to eliminate sulfides. The HSES is based on a specialty redox regenerative process. Redox is the reduction oxidation reaction that uses those chemistries to specifically target reduced sulfur compounds in the water, air, or sludge. Now, on a deeper level, we have step one, the reduction phase. On the top left, you have H2S present, and when you inject the Hydrex catalyst of the HSES, the Hydrex catalyst in its original state is in the form of Fe3, or ferric, which we call a lean chelated iron. And when the H2S and lean catalyst react, it instantly spins off the elemental sulfur chain. It reduces the lean Fe3 catalyst to Fe2, or ferrous, which we refer to as a rich chelated iron because it's taken on the sulfur. Now, as Phil said, in a typical iron salt, this would then drop out as a solid once it's sequestered to sulfide. However, with the chelated iron complex, it needs a simple oxygen source to regenerate. We use hydrogen peroxide mostly as the oxidant, but sometimes oxygen could be used if it's needed. Step two, the oxidation phase, when the oxygen source reacts with the rich Fe2, it regenerates itself back to a lean Fe3, and the process is repeated over and over again until there's no presence of sulfides, and it starts back again at the reduction phase, with the only byproducts of the process being elemental sulfur, dissolved oxygen, and water, which is simply the breakdown of hydrogen peroxide. Now, another way to look at HSES in a pipe from left to right with the injection to the completion is what HSES would do in your water. Mimicking a headworks or a lift station, for example, just as shown, the process is simply reducing Fe3 to Fe2 and regenerating an oxygen source, performing this reaction over and over again until there are no sulfides present. The graph is a simple representation of the effectiveness and rapid reduction of sulfides when applied. Now on the right is a picture of Hydrex catalyst on the top and sulfur byproduct, and it's simply a visual representation of the lean Fe3 reacting with the H2S to create elemental sulfur. So we just provided a detailed review of the process. Now we'll show you a simple video explaining it further and illustrate the process better. The H2S uses chemical metering pumps and storage tanks. We dose the two Hydrex chemistries using a PLC to provide real-time vapor phase H2S readings to ensure efficient dosing of the chemicals. The chemistry is dosed with the two pumps separately until they are injected into the water stream. Then they become thoroughly mixed together, creating the redox reaction. Now, from a molecular point of view, the first step, the reduction phase, the Hydrex catalyst removes electrons from sulfide molecule and converts them into sulfide and elemental sulfur, which can't be formed back into sulfide. The second step of the oxidation phase, the Hydrex catalyst reacts with the Hydrex oxidant, converts back to original state, ready to reduce another sulfide molecule. H2S is a very powerful liquid redox process that reduces sulfides to elemental sulfur within 3 to 5 minutes and regenerates itself over for 2 to 4 hours. It's green, biodegradable, and a safe method of quickly eliminating H2S and other reducing sulfur compounds. Now, just as we showed in the video, the process is a simple 2-tank, 2-pump installation with a PLC for remote monitoring and automation capabilities. As you can see here, larger tanks are double-walled HDPE bulk storage tanks for peroxide, and the smaller tanks are single-walled HDPE for the catalyst. Depending on the application and the complexity, the pilot is just as simple. We ship out a plastic tote that contains pumps, PLC, sensors. Sometimes it's necessary to tap a line with a saddle and 2 injection points for the pilots. Most of the time, we can add them in a wet well or an area of mixing would be sufficient. We've used more complex sampling in manholes when needed for H2S sampling. And in some cases where power is an issue, we've utilized a solar option for the PLC for remote monitoring and feed control. Pilots are performed with either drums or totes of chemical, and we use proper spill protection containments when necessary. So now that we've spoken a lot about how we can treat H2S in the water, now let's talk a little bit about how we can treat H2S in the air. So as we discussed, wet chemical scrubbers use chlorine and caustic to treat H2S. And in a chemical scrubber, we can retrofit and replace the chlorine and caustic with the catalyst. Now, the constant presence of oxygen around 19.5%, we use that ambient air as the oxygen source to complete the reaction. The back and forth between the conversion of Fe3 and Fe2 being regenerated with the ambient air being pulled in allows the catalyst to continue to regenerate and last for a period of time between 60 to 90 days. Now, where a typical caustic bleach wet scrubber is referred to as a feed and bleed of the chemicals, we simply close the drain of the sump. We allow the catalyst to recirculate the same way the chlorine and caustic does with a small amount of makeup water using the recirculation pump of the existing scrubber. Therefore, zero capex is needed because we are simply replacing the chemicals used. Now, this also eliminates the need for the chemical dosing pumps and the storage tanks used by those chlorine and caustic storage handlers. It also reduces the amount of fills of chemistry of the catalyst versus many deliveries of caustic and bleach throughout the year. Now, one special thing is we have no fouling of the media because the vast majority of the H2S is converted to thiosulfate, which stays in suspension and will not attach to the plastic media. Therefore, the need for routine acid cleanings is significantly reduced or eliminated. And because the media doesn't foul, we take away the additional capex of having to purchase new media, or that can be highly reduced. Now, if you're looking for a simple scrubber design, we have that too. This scrubber installed at a wet well is a 400 SCFM one treatment stage scrubber that can pack a punch. It has just the right amount of catalyst in the sump to do the job for 60 to 90 days and can handle up to 1,000 ppm of incoming H2S. It uses the same vertical packed bed tower plastic media that chemical scrubbers use, with advanced instrumentation and communication that enable it to be operated and monitored remotely if desired. The design incorporates a lot of operator-friendly accessories to make the monitoring and maintenance of the scrubber easier to help and minimize potential downtime. Now, you've seen many benefits to the H2S process. I'll recap those. Highly selective to sulfides. It's environmentally friendly, it's non-toxic and biodegradable product. It's not harmful to beneficial bacteria. It's safe to handle, easy to operate, pH neutral. It's a redox reaction that's highly efficient in lowering OPEX. Therefore, it lowers the volume of chemical demand and dosage rates and reduces the amount of deliveries, labor, equipment, and the carbon footprint. We automate the system to use the best control of the dosing, and we can integrate that into your existing SCADA system. So now we'll talk about some case studies where we've piloted and implemented the H2S in both industrial and municipal applications. And I'll turn it back over to Phil to talk about the first one.
Thanks, Jeff. This first case study was a soy plant in the Midwest, and this facility was experiencing severe odor issues due to H2S, and it was resulting in higher than acceptable corrosion rates, both at the soy plant itself and at the Muni headworks. There was also concerns about the potential for employee health and safety risk associated with those higher H2S levels. These were experienced at both the municipality receiving the water and the soy plant that was sending it. So the key drivers were the employees' health and safety, and secondarily, of course, corrosion prevention. At the beginning of this, we were running H2S levels at the soy plant outfall, which is where the chemistry was later was added, of greater than 1,000 ppm. So as you know, at greater than 1,000 ppm, this is a deadly level. And then at the POTW headworks, they are experiencing greater than 20 ppm at the receiving site. The graphs to the left came off of the Acrolog H2S logger, data logger that was put into the wet wells, both at the injection point at the plant, right after the injection point at the plant, and then downstream at the headworks. And if you notice on the upper left side where it says overscale, that is where we were running over the 1,000 ppm of H2S before the treatment was begun. Then the Hydrex solution started and it dropped down to getting levels that were down at the very bottom of the chart. That happened within about 3 hours, and those levels were just a couple of ppm. And that is at the plant site. Downstream at the headworks, they initially started up around 40, and after we initiated the treatment, we were able to get them down into the single digit as well. If you notice about halfway through, though, on that lower chart, the numbers did come back up, and that's pretty common because that's the mixing of untreated municipal wastewater back into the stream that we had already treated. However, when they got below 20 ppm at the headworks, they were happy with the results, so this was doing enough of what they needed to have done. So we had the sulfide elimination system. We used an advanced automated control system and 2 data logging H2S monitors. And the results were 0 ppm at the soy plant, less than 10 from our contribution to the municipal plant. We reduced the infrastructure corrosion and provided a safer work environment at the plant and at the headworks of the POTW. Jeff, will you take the next one?
So on a municipal side, this is a typical that someone sees where you're treating a wet well in the collection system, sometimes at a headworks. Well, with this one in Southeast United States, we had a wet well that was adjacent to a busy retail location, and it was producing offensive odors, and it was causing many, many odor complaints. And what we found is multiple upstream lift stations were the culprit that was causing this high levels of H2S and odor complaints. It was a huge safety and infrastructure issue. So the influent flow for these multiple lift stations was approximately 500,000 gallons per day. We found anywhere from 400 to 1,000 ppm of influent H2S that were in all three of these lift stations, doing an analysis anywhere from 10 to 20 milligrams liter of sulfide. So as you can see, all these lift stations were extremely high levels of H2S. Lift station C was the retail location. It had 1,000 ppm of H2S that we were monitoring. After we did some treatment upstream, we were able to get that down to 20, and I'll talk more about what that goal was. Lift station B was where we did most of the treatment. We initially dosed there using a PLC to automate and control those chemistries based off of real-time H2S. 500 was around what came in for the average influent, and we were able to get that down to 40. Now, what we found upstream, there was another lift station A. It was experiencing the same high levels of H2S, anywhere from 400 to 1,000 before we treated. And after we treated, we were able to get those down to 10, which helped the lift station B to control down to lift station C. So the goal here was to monitor lift station C and keep those H2S levels under 50 to reduce the odor complaints that were occurring. Not down to 0, not down to 10, but under 50, just to maintain that we could take care of those offensive odors. So overall, we accomplished this and provided an effective solution to control the odors. They reduced the odor complaints and provided a solution to extend the infrastructure life of the wet well. Now, these two graphs is data collected from 2 of those lift stations showing the high levels of H2S prior to starting the injection of the HSES. And after some optimization and tweaks of the dose rates, the end result was a significant reduction in H2S at both lift station A and lift station C. You can see that with lift station A, peaks in the 350, we optimized and got it down to where it was in the 20s and under 50 where we needed to be there. And then with lift station C, they were experiencing 500 inlet, and we optimized that down to where we were between 50 and 100, which was the overall goal. Now, Phil talked a little bit about treating H2S in the sludge. Well, this is another example of where we had a municipal wastewater treatment plant, and they had a sludge dewatering processing in a central Ohio wastewater plant. They were simply looking for a better solution for their offensive odors and malodorous compounds in the dewatering building that was coming from the belt press sludge operation, but it was filtering over into the admin and the lab. So they were looking for something that could take care of those odors, safer for their workers, but a simple to install solution. The influent flow for the plant is about 5 million gallons per day. And the belt press operates around 150 gallons per minute. Now, while H2S was minimal, the odors were very offensive and they were affecting the environment. So Veolia Water Technologies replaced a chlorine-based product that was being fed in the sludge line between the holding tank and the belt press. It was a simple 2-pump, 2-tote delivery of HSES because the customer did not want to have huge bulk tanks. He wanted a simple design. And within a matter of minutes of turning on the system, the odors improved significantly, and there were no offensive odors present that filtered out of the dewatering building into the admin and into the lab. Now, they did see a slight reduction in polymer usage due to using the HSES over the chlorine-based product. It was a simple setup and installation for them, and they actually saw a reduction in OPEX over the previous treatment program. So now that we've talked about issues with H2S, how do you get started? When do you consider and how to ensure the right solution for your H2S or odor control project? Regardless of what you do, there's many drivers. to try and control H2S and other odor control initiatives. Whether you're an industry or a municipality, public health, welfare, and legislation can drive the issue. Or you could have a unsafe working environment for your employees. You could have extensive effect on infrastructure, which we've talked about, which is corrosiveness. And of course, the biggest driver is the community and odor complaints. Many industries or municipalities have to provide that goodwill to their ratepayers, or a license to operate, if you will. So if you have one of these issues or others, you need to get started somewhere. So how do you get started? How do you get started trying to tackle your odor or H2S issue? Well, there's key drivers or goals that need to be looked at. What is the application? Well, we've talked about treating H2S in the water, in sludge, as well as air. Well, is it a headworks at the plant? Is it a lift station in the collection system? Is it the produced water at the industrial facility, a retention pond, dewatering, digesters, etc.? Well, the first thing we need to do is we need to collect some data. So for example, treating water, we need to know the flow rate of the issue, the hydraulic detention time, what's the temperature, what's the pH. The more information we get, the better. Second, we need actual dissolved sulfide amounts in milligrams per liter in the water. We need atmospheric data in H2S for historical trends. And then third, what are your goals? As you've seen, it could be to completely eliminate H2S to zero. It could be to maintain a lower concentration, or it could be to control offensive odors better. So how do we get the data we need? Well, we use instruments like these to measure dissolved sulfides in the water. Once we have the dissolved sulfides, flow, and detention time, we can then calculate how much sulfur is in the water and determine how much chemistry is needed to perform a pilot. We also use H2S sensors to monitor the atmospheric H2S levels and record this prior to performing a pilot so we can understand the diurnal and averages and peaks of what we're trying to treat. Understand, are there any outlier laterals or influences that would affect the treatment? And lastly, we provide real-time PLC-driven remote monitoring and automation to be able to see the influent and effluent H2S and make those simple changes remotely, providing a smart approach and the most efficient use of chemistry for the best results and cost savings to the end user. So to briefly summarize, H2S and odor are an issue in both industry and municipalities, and there are many methods to handle this. We have a solution with H2S redox process that can handle your needs very quickly and effectively. So contact us and we can understand your problem and help you implement a simple solution that could be the right fit for you. Thank you so much for all your time, and I'll now turn it back over to TJ where he can discuss any questions you may have.
Great, thank you so much, Jeff. Thank you, Phil, for sharing all of that that experience and those case studies as well regarding the Hydrex Sulfide Elimination System. I just want to remind everyone there's that question pin on the right side of your screen. We're going to stay on for a couple more minutes here and get to some of these questions that we have. We have some already that we'll start to get to. Just one blanket question. The recording of today's webinar will be sent tomorrow. There's a lot of questions about that. So you can go watch and have access to those slides when watching the recording when that comes out in your follow-up email tomorrow. So again, feel free to enter your question in that panel and we'll get to as many as possible. Just to get things started here on some technical questions that we received. Let me look here. I guess one question that we had here is, what are your thoughts on using potassium permanganate to oxidize H2S in water? Jeff, do you have any comments about that?
Probably going to turn that one over to Phil. He's, I think, more familiar with that.
In my experience, I have seen it used or attempted to be used. The customers that I had that were using it were more concerned about the cost, but most importantly about the safety issues related to it. It is a form of an oxidizer, and if done correctly, it will work. However, the cost and the risk associated with playing with it was the reason that they moved away from it.
Okay. Thanks for that, Phil. A question that is really interesting too is if you could dose this solution, the HSS solution, before your biological treatment, whether it be anaerobic or aerobic. We have some questions about that. Can you comment on that?
Yeah, typically if you have your standard COD and BOD, we're going to be able to take care of the sulfides in solution. Let's say you're at a headworks, and with the quick reaction of the sulfides being eliminated in 3 to 4 minutes, you're simply using up the peroxide in 2 to 4 hours through the primary. So if you treat into a headworks, into a grit, through into your primaries, you're using up the treatment, and your byproducts are simply dissolved oxygen, water, and elemental sulfur, which by the end of the primaries, there's no effect on any treatment issues with the plant.
Great. Also, there's a question about what HSS target is. Is it selective for H2S in the presence of other reduced compounds such as other organics? Can you answer that, Jeff?
On a simple way, it's selective to sulfides, but it's hitting all reduced sulfur compounds. So Phil can probably talk more to all the different compounds, but it goes after sulfide first. But there's other reducing compounds that don't cause H2S. It doesn't cause the safety impact, but it does cause the odor impacts.
So when we've been using the term H2S, it does, we should have said in the very beginning, it does impact the mercaptans as well. There's a whole bunch of other sulfide species that it will take care of as well. H2S is the one that gets the attention, although especially in chemical plants, there may be other reduced sulfur species that we need to attack, and this chemistry will go after it.
Great. An application question, I'll give it to you, Phil. Can you talk about a settling pond with variable flows and how this solution might be able to work? Specifically, it's saying that with H2S levels of 50 ppm in a large volume of water as well, how could HSS work in that particular application?
Just one thing that we did do that I was involved with is a way to do it is typically in the settling pond, if you've got no complaints with the water until you draw the water out of it and send it to the POTW, and that water is laden with H2S, we can do treatment as soon as it comes out of the pond. If we know we have H2S that's going in the water, going into the pond, it could be treated there. Typically, settling ponds, if they have a lot of H2S problems because everything settles down and it's become anaerobic or anoxic at the bottom of the pond, sometimes that is a good application for blowers or for mixers to try to get that stuff back up to the top where it can be treated.
And great. And then while we're talking about applications, Phil, can you comment on the possibility of this being used at refineries for wastewater treatment?
So certainly it could be used at the refineries for wastewater itself. And typically in a refinery, after you've got the true wastewater, after you've taken all your slop oils and you've moved them over somewhere else and you just have the wastewater treatment, if you still have H2S there and it may be poisoning the biological bed or creating a problem, this could be fed at the front end, maybe on the way into an EQ tank or out of the EQ tank on the way to the process, so that we get rid of the H2S or convert it to sulfides before it hits the rest of the process.
Okay. Jeff, a question for you is this particular asker was saying that they were interested in doing treatment at a discharge of a sludge pump, which then goes to a screw press. It looks like that there's only 3-minute times between the pump to press. And I guess the question is asking, will the redox process be efficient enough to be effective in that application?
Absolutely. All we need is 3 to 5 minutes of mixing and reaction time to break down the sulfides. So that would work with no problem.
Okay. If we go back to sulfides in anaerobic digestion process, what is the impact of removing that sulfur in anaerobic digestion, and is there any change?
Bill, do you want to take that one?
So impact of the conversion of H2S to sulfide would have a positive impact because you're not going to let the bed get toxic. Sometimes you could have such a high level of H2S that it does impact anaerobic processes. So by getting rid of it, it's actually beneficial. The chemistries themselves are not going to affect the bacteria that's in the anaerobic process, like such as a tertiary treatment. So the product would be beneficial, especially if H2S is impacting their ability to either process or to discharge from an anaerobic process from a digester. And this is a technology that is becoming more and more common in the poultry industry and other places that are trying to do things such as making methane gas from the waste that they collect and trying to digest and make methane gas. This is an excellent way to do it so that you're not commingling your clean methane gas with H2S, which creates a sour gas, a corrosive sour gas. So definitely this is beneficial on that end of it if you're trying to create a product that you want to have free of H2S.
Thanks, Phil. Jeff, a question is that sulfur that drops out through this reaction, what happens to that sulfur? How is it collected? Can it be used as a byproduct? Can you comment on that a little bit?
In the municipal and the industrial, applications, while there is a lot of H2S in the influent, that elemental sulfur stays in solution and it doesn't drop out. When you flip over to oil and gas, when there are high levels of H2S, 400,000 that you're trying to pull out of the ground, now you actually are dewatering the sulfur just like you do water, and it can be a biosolid that can be land applied. But on the municipal and industrial side, it stays in solution.
Let me add to that a little bit too. In the upstream side, this technology is used, but in a different way. It's a little bit more equipment specific, and it's almost more of a dry process versus a wet process. And sulfur that is removed there is a product that some people have an interest in purchasing and using. So, but that's starting with very, very high levels to begin with, whereas typically in water phase, municipal and industrial, the numbers aren't that excessive where you could create a dry product that you could sell.
Great, thank you both for that. So we have time for one or two more quick questions. What is the recommendation for real-time H2S monitoring in terms of in the liquid or even in the air? Is that something that you could recommend? You had that slide about some of the equipment that you use. Can you comment on that, Jeff?
What we've used is we have a simple PLC, and we use the AcroLog H2S sensors to record real-time atmospheric H2S. And that atmospheric H2S, based on what level we're trying to limit down to, it is then driven by the pumps. And then the pumps will drive the chemistry, and that will create the demand. And so in an instance like a wet well where you have a pump, we will tap into the pump and we will tap into the receptacles that are at that, and we'll put the pumps in there. And so when the pumps are energized, the chemicals come on. That's another way we automate. It's a little difficult to measure dissolved sulfide in the water on a real-time basis. We're looking at more atmospheric, and that's what's controlling the feed rate and the levels.
The treatment process could be as simple as a couple of totes and a couple of pumps, all the way up to the next phase may be a PLC that feeds chemistry, double the dosage during the peak periods. If you know that every day at noon I get a slug and every day at midnight I get a slug. We do and have where we can put a analyzer downstream and use it to talk to the cloud and come back down to a feed system that's upstream, so we can proportionally feed the chemistry to the H2S levels that are in the air. And you could certainly do it based on flow as well. If you have a more continuous H2S level coming out of a facility, you could base it on flow. So your normal, the sensors are specific to H2S. That's the specialty. After that, the rest of the control scheme is just PLCs and regular logic.
Okay. Well, we're sort of winding this webinar down. That's going to be it for our question and answer period. Thank you both for fielding all those questions. And if there's something that pops up after the webinar, feel free to reach out to myself or even one of the presenters. You can connect to them on LinkedIn or look them up via email. I just want to remind everyone, please take that survey after the webinar. Your feedback is critical to us to continually improve these webinar presentations. We go over the feedback in detail and make sure the next one continues to always improve. So thank you in advance for doing that. And lastly, I just want to take one moment to thank our two panelists, Jeff and Phil, for spending the time and preparing all of this content and sharing their experience with us. But also, most importantly, I want to thank everyone who spent an hour of their day to join us to learn a little bit more about odor control and H2S, and of course, the Hydrex Sulfide Elimination System. So at this time, the webinar is complete, and I look forward to seeing you on a future presentation broadcast. Thank you, and have a great day.